Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 3 of our unit Mechanical Properties of Solids. So let's begin with today's class. In today's class first we are going to discuss about the thermal stress. So let's begin. What is thermal stress? Let's assume that these two are the rigid support, and between these two rigid support one of the rod has been fixed, as you can see in this figure, that if a rod is fixed between two rigid supports, now what happens, I am going to heat this rod. I am going to provide a temperature difference to this rod. Due to change in temperature, its length is going to change, and so it will exert a normal stress on the supports. This stress is called as the thermal stress. Now, how could I find out the value of this thermal stress? What I understand is it's a Young's modulus would be equals to stress divided by strain. So from this I can write this. It's a thermal stress is equals to Young's modulus multiplied by thermal strain. But when I write its thermal strain, it is basically a delta L by L. And in the thermal properties of matter, you have learned this. It's an alpha is equals to delta L divided by L delta theta. So from this delta L by L, it's a alpha delta theta. So from this, it's a thermal stress. That could be, this thermal stress could be written as y into alpha into delta theta. It's a y into alpha into delta theta. And from this thermal force, it's a y into a into alpha into delta theta, where alpha is linear temperature coefficient. It's a linear temperature coefficient of expansion. This is what we call as an alpha. I hope this is clear. Is it clear? So this is the situation when this rod is being fixed between two rigid supports, and when I'm going to heat up this rod, that this rod wants to increase its dimension, but it is not capable enough to increase. Why? Because it has been fixed between two supports. So the stress, the force it faces, that is what we call as a thermal stress or thermal force. I hope this is clear. Is it clear? Now let's suppose, if I look at this in a phase of a volume expansion, then thermal stress could be written as it's an k into gamma into delta theta, where k is the bulk modulus and gamma is the coefficient of cubical expansion, and delta theta, that is equals to the change in temperature. I hope this is clear. Is it? Great. So now let's ready for the numericals based on this. Let's have a look. Let's look at this. Suppose this are rigid supports, and within this rigid support our rod has been fixed, and this rod is being heated from this source of supply. So if if temperature difference if temperature difference of 30 degrees Celsius is applied across the roads, find out thermal stress acting on the root. You need to find out the thermal stress acting on the road. So while I do this, let's suppose they have given me one more thing. It's an alpha, which is equals to 3 into 10 to the power minus of 5 Kelvin inverse, and the Young's modulus, that is equals to 5 into 10 to the power 5. It's a Newton per meter square. So what I need to find out, I need to find out the thermal stress. And if I need to find out the thermal stress, then the situation will be that this thermal stress will equals to, this is equals to, it's a y multiplied by alpha multiplied by delta theta. So y, let's put up the value. It's a 5 into 10 to the power 5 multiplied by alpha, which is equals to 3 into 10 to the power minus of 5 multiplied by delta theta. And this delta theta, it's a 30 degrees Celsius. So this is equals to, this has gone, this has gone, and this is 5 threes are 15 multiplied by 30. It's a 450. It is a stress, so it should be a Newton per meter square. I hope this is clear. What was your answer? Was it same? Was it? Are you sure? Are you sure? Are you sure? Great. So ready for one more numerical based on same concept. Are you ready? Let's have a look. The next question. Let's suppose one of the road is there and it has been kept over this, and let's suppose it has being heated from a flame. So the question says that temperature difference if temperature difference is being applied across roads, across being applied across the roads, find thermal stress acting on it. Here Young's modulus, it's a 5 into 10 to the power 5 Newton per meter square. Alpha, it's a 3 into 10 to the power minus of 5 Kelvin inverse. And delta theta, it's let's say 10 degrees Celsius. So what is to be done is that this thermal stress should be is equals to y into alpha into delta theta. And when I write this, it's a 5 into 10 to the power 5 multiplied by 3 into 10 to the power minus of 5 multiplied by 10. It would be 5 threes are 15 into 10, it's a 150, and this has been gone. Newton per meter square. Have you did this? Have you? Have you did this? If yes, then this is incorrect one. This is not to be done in this case. Why? Give me the answer of my question. Does this road being fixed by any supports? Does this road is being fixed by any support? Is it? Your answer should be no. If no, then why thermal stress will develop? There is no provision of thermal stress if this road is free to expand itself. So when this is going to be heated, when this is going to be heated, this will extend its dimension either in this side or in this side. I hope you understand this. And if it is allowed to extend itself, if it is allowed to extend itself, there is no need to express a thermal stress based on this. So in this case, a thermal stress will be 0 Newton per meter square. This has been asked in J mains. I'm serious. But do you understand this? Please go through the data. Thermal stress is being developed in this situation. Look at this. This road has been supported by this two rigid supports, or when we have used the applications of this thermal stress. Look at this. A rigid support is there, and this road is being supported by these two rigid supports. Here, here no rigid support is there. No fixing of the roads are there. That means no thermal stress will be there, because if I'm going to be heated, if this road is going to be heated, then this road will expand itself. I hope this is clear. Is it clear? Great. So please keep this in mind. Let's look at the next application. It's a force between the two roads. Let's suppose understand that two roads of different metals having the same area of the cross section A, and they are placed end to end between two walls, as you can see in the figure that this is the one of the road, this one is the one first road, this one is the second road. First road is having the length L1, its Young's modulus is Y1, and its coefficient of linear expansion is alpha 1. Same way, a second road is having a length L2, its Young's modulus would be the Y2, and its coefficients of linear expansion is alpha 2. Now let's suppose if the temperature of both the roads is now raised by the temperature T degree. So it is something like that if I'm going to heat up this by the temperature of T degree, then what will be the situation? In this case, as this has been supported by two rigid supports, it wants to increase its length, but this is not possible. So let's understand what the situation will be. So increase in length of the composite rods due to heating, that will be equals to L1 plus L2, and when I say it's an L1 plus L2, this L is equals to L alpha delta T. So this is equals to L1 alpha 1 plus L2 alpha 2 into T, because they have been heated by the same temperature, and this has been written from the L alpha delta theta. And due to compressive force F from the walls due to elasticity, decrease in length of the composite rod, that will be equals to when I say delta L, this is equals to FL by A into Y. We have this relation, it's a Y is equals to FL by A delta L. From this, it's a delta L which is equals to FL by AY. So I'm going to write the same thing, that A is equals to sorry, it's an F by A into bracket L by Y, but L by Y would be equals to L1 by Y1 plus L2 by Y2. So as as the length of the composite rod remains unchanged, the increase in length due to heating must be equal to the decrease in length due to the compression, and that's why this could be written as F by A into bracket L1 by Y1 plus L2 by Y2. That should be equals to L1 alpha 1 plus L2 alpha 2 into T. Or from this I can have the value of this force. It's an A into bracket L1 alpha 1 plus L2 alpha 2 into T divided by L1 by Y1 plus L2 by Y2. Please keep this in mind. This is a very fresh applications, and this has not been asked anywhere. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Great. Now let's understand a different parameter of to understand the solids. It's a force constant of wire. So when I say it's a force constant of wire, we say that force is required to produce unit elongation in a wire. That is what we call as a force constant of that material of the wire, and it is going to be denoted by K. So we have even used this application before as well. In that time we were used the Hooke's law. It's an F is equals to K into X, where F is the applied force and X is the extension, or I should say expansion, or it would be an compression in that cases. So now here also it's a K is equals to F by delta A, and we have the relations of the Young's modulus, which says it's an F by A divided by delta L by L. So from this it should be an F by delta L, that is equals to F by delta L, that is equals to YA by L. So from this this K is what we call as the force constant It's a force constant of wire, and its value would be equals to y into a divided by L. This is the force constant of a wire. Do you understand this? Do you? Do you understand this? Great. So, are you ready for the questions based on the force constant of a wire? Are you sure? Let's have a look. So, first question. If force of 3 into 10 to the power 3 Newton is applied on a wire which changes the length of the wire, by 10 centimeter, find out force constant of wire. So how will you do this? I have been provided the force, and that force is equals to 3 into 10 to the power 3 Newton. I have been provided the expansion that we call as a delta L. This is equals to 10 centimeter, but this is in centimeter, this is in Newton, so this is going to be changed. This would be 10 into 10 to the power minus of 2 meter. Now I am having the relation which is equals to F is equals to K into delta L. From this, it's a K which is equals to F by delta L. So this is 3 into 10 to the power 3 divided by, it's a 10 into 10 to the power minus 1, it's a 10 to the power minus 1. This is equals to 3 into 10 to the power 4. It's a Newton per meter. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? Do you have any doubts up till now? Is there anything? Is there? Do you have anything? No? Great. Now, let's discuss one very important aspect to understand and to learn the force constant. It's a very important informations about the force constant of a wire, that we can use force constant of a wire as we are using spring constant, the spring constant. So if I denote, if we denote force constant by, let's say, K, then if two wires are connected in series, then the force constant equivalent, a force constant equivalent could be written as, this is equals to 1 by k1 plus 1 by k2 up to 1 by kn if more than two wires have been connected in series. Same way, wires are if wires are connected in parallel then their force constant or their equivalent force constant can be given as, this could be given as, this is equals to K equivalent is equals to K1 plus K2 plus K3 up to Kn. I hope this is clear. Is it clear? Is it clear? So now do you understand how to use a force constant? Are you sure? Would you like to have one of the question? Let's have a look. Let's suppose there are two wires. This are the two wires, and let's suppose a length of this wire is L, cross sectional area is A, and its Young's modulus would be a Y1. Another wire having length L, cross sectional area A, and its Young's modulus is Y2. M mass of object has been hung with these two wires. So they will ask me that find out equivalent force constant of this wires. So first thing, what I understand is do this are connected in series or parallel? Do these two wires are connected in series or parallel? Yes, as they are connected in parallel combination. So when they are connected in parallel combination, what I am having, it's a K is equals to K1 plus K2, while force constant K, that would be equals to YA by L. When I say it's a force constant, this is equals to Y into A divided by L. So the situation is that when I use K, it would be equals to Y into A by L. So this could be written as this is something, this K equivalent. So this would be, it's a Y1 into A plus Y2 into A divided by L. That should be is equals to, it is Y1 A divided by L plus Y2 into A divided by L. I hope this is clear. Is it clear? Is it clear? But if I'm going to use this, it's a thicker wire, and if it is a thicker wire, this totality this totality could give me the next amount of volume, a next amount of cross sectional area. I hope you understand what I mean. Do you understand it? Do you? This is the K equivalent, or this could be written as, this K equivalent could be calculated as Y1 into A divided by L plus Y2 into A divided by L. I hope this is clear. Is it clear? So this can be used very effectively, and this is very helpful to calculate a certain applications of the numericals. I hope this is clear. Is it clear? Great. Now let's look at certain quick questions. It is the force required to produce a unit elongation of a wire. It's a force required to produce a unit elongation of a wire is called as the blank of the material of the wire. So it is the force required to produce unit elongation. It's a force divided by elongation of a wire. Yes, it is known as the force constant. It's an F by X that generally we represented by K. Next, when when there is a change in length, due to change in the temperature, the stress is called as thermal stress. This is the thermal stress. I hope this is clear. So now, do you have any problem regarding Young's modulus? Do you have any problem? Do you understand it completely? Have you got it correctly? Are you sure? Are you? Great. Now let's discuss what is bulk modulus, generally denoted by capital B. This is the bulk modulus. Let's have a look. When I say bulk modulus, it is defined as the ratio of the volume stress to the volume strain within an elastic limit. So this B, that would be equals to volume stress divided by volume strain. As you can see this, that on this object, a force is being taken and force is being acted from every directions, and this force is acting perpendicular to the surface. You can check this at each and every point. So when a solid or when a solid or fluid is subjected to a change in pressure, its volume is going to changes, but the shape remains unchanged. Yes, this the force per unit area applied normally and uniformly to the surface of the body that we call as a pressure gives the stress, and change in volume per unit volume gives the volume strain. When I say it's strain, it's a change in dimensions divided by original dimensions. So thus, if the volume V of the body decreases by an amount of delta V, when the pressure on its surface is increased uniformly by delta P, then in equilibrium, when I say volume stress, it is an F by A, which we write as a delta P. When I say volume strain, it is minus of delta V by V. And if I take a ratio of this, if I take a ratio of this bulk modulus that we call as a volume stress divide by volume strain, this would be equals to minus of delta P divided by delta V by V. And if I write it's a minus of delta P divided by delta V by V, this could be written as minus of V into delta P divided by delta V. When I use a negative sign, this shows that with increase in pressure, the volume decreases. SI unit, if I look at this according to the dimensions, this delta V by V is the dimensionless. So SI unit of this bulk modulus is same as the Newton per meter square. Or if I look for the CGS unit, it's a dyne per centimeter square. And its dimensions, it's an M1 L minus 1 T minus 2. Is it clear? Great. Now let's understand one more property. It's a compressibility, which is basically a reciprocal of the bulk modulus. And when I say it's a reciprocal of bulk modulus, that is known as compressibility. So compressibility, it is equals to 1 by B, and it is equals to minus of 1 by V into delta V by delta P. SI unit, it's a meter square per Newton, or CGS of that will be equals to centimeter square per dyne. This is the situation. It's a centimeter square per dyne, and its dimensional formula. Is it's an M minus 1 L1 T2. I hope this is clear. Is it clear? Any doubts up till now? Is there? No? Let's look at the quick questions. It's a reciprocal. Reciprocal of the bulk modulus is known as the, yes, it is the compressibility. Next, in the formula of bulk modulus of elasticity, the negative sign indicates that increase in pressure always causes a blank in volume. Yes, decrease in the volume, it is something like this B is equals to minus of delta P divided by delta V by V. Is it clear? Is it? Are you sure? Great. Next, the units and dimensions of the bulk modulus of elasticity. Yes, it's a Newton per meter square, and its a dimension, it's an M1 L minus 1 T minus 2. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Do you have any doubts up till now? Is there anything? Is there? No? Then ready for the questions? Let's have a look. Let's understand that suppose a container is there, and this container has been filled with this fluid, and on this fluid a piston is there. Let's suppose one of the piston is there, and in this We have kept one of the sphere. If I shift my piston in the downward direction, they will ask me that find out change in radius of the sphere when when piston is going to press the fluid. So what will happen? What do you think? When I'm supposed to push this, and this piston is going to push the fluid, and this fluid is going to push the sphere, and as if it is going to push, or if it is going to apply a pressure on the sphere, then this sphere is having a force from every direction. What I need to find out, I need to find out the change in the radius of the sphere. So what I can write is that it would be equals to B is equals to minus of delta P divided by delta V by V. I understand that it's from delta V by V, that could be written as 3 times of delta R by R. I hope you are okay with this. Are you? No? Let's look at this. It's a volume. It's a volume of the sphere. It's a 4 by 3 pi r cube. From this, that we understood that delta V by V, this is equals to 3 times of delta R by R. So now, are you okay with this? Great. So what I need to do is, it's a B, that is equals to minus of delta P divided by delta V by V. If I replace the value of delta V by V, this is equals to minus of delta P divided by 3 times of delta R by R. This is bulk modulus. So from this, it's a delta R by R is equals to minus of delta P divided by 3B. That's it. You did it. Great job. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now, ready for the next question? Are you? Let's have a look. If they said that, let us suppose it is something like this, and this has been filled with one of the fluids, and object has been placed over here, something like this. This height is the 10 meter. So, and if this object, let's make it simple, if this object is considered as a sphere, then find out, they will say me that find out bulk modulus, find out bulk modulus of this sphere if it has been changed, if it has been changed by its volume by 1%. This height is given, and this density of the fluid, is, let's say, it's a 1050 kg per meter cube, and you can take G is equals to 10 meter per second square. You need to find out the bulk modulus of the sphere. How will you do this? What is to be done? What do you think? What is going on in your mind? How will you do this? Any idea? Is there anything? Is there? No? Let me help you. That this B could be written as minus of delta P divided by delta V by V. Here delta P would be provided by the fluid pressure, and if I take the fluid pressure, it's an H into rho into G divided by delta V by V. So if this is the situation, then this will be H is equals to 10. Density of fluid, it's a 1050, multiplied by G, it is a 10, divide by this delta V by V, it's a 1%, so it's a 1 by 100, and this is multiplied by 100. So this is equals to 105 multiplied by 2 plus 1 3 plus 1 4 plus 1 5. It's a 105 into 10 to the power 5 Newton per meter square. That's it. You did a great job. I hope this is clear. Is it clear? Is it? Are you sure? So now do you have any doubts up till now? Do you have any doubts up till now? Is there anything? Is there? Are you sure? Are you? Great. So let's understand isothermal and adiabatic bulk modulus of elasticity, as well as we are going to observe also the different elasticity for the different processes of gases. First, let's begin with the isothermal bulk modulus of elasticity. The bulk modulus of a gas in isothermal condition is defined as the isothermal bulk modulus of elasticity. So when I write isothermal process, it is always when I said it's an isothermal, then you must understand that in this process a temperature remains constant. So this will be the situation, and if temperature remains the constant, I can write it's a P into V is equals to constant. So if I differentiate on both the sides, it would be a P dV plus V dP is equals to 0. So from this, it's a P dV is equals to minus of V dP. And what is B? This bulk modulus is equals to minus of delta P divided by delta V by V. So this is minus of dP divided by dV by V. That is what we call as a P. So this bulk modulus would be equals to P. So for the isothermal process, its a bulk modulus of elasticity is equals to the pressure of a gas, I hope this is clear. Same way on a similar parallel track, we can find out the adiabatic bulk modulus of elasticity. So when I calculate the adiabatic bulk modulus of elasticity, I understand that the bulk modulus of a gas in an adiabatic condition is defined as the adiabatic bulk modulus of elasticity. For adiabatic process, you understand that this is P into V to the power gamma, that is equals to constant. So if I am going to differentiate it on both the sides, then I will have it's a P into gamma into bracket V to the power gamma minus 1 dV plus V to the power gamma dP is equals to 0. So if I'm going to solve this, this is what I received. It's a minus of dP by dV by V. This is equals to gamma into P. So it's an adiabatic elasticity of a gas, that would be equals to gamma into P. Hence adiabatic bulk modulus of elasticity is equals to the gamma times of pressure. So if someone has asked me about the ratio of adiabatic to to isothermal elasticity, then it would be an adiabatic elasticity gamma times pressure. Isothermal elasticity, it's a pressure, and their ratio would be only the gamma, and gamma is always 1. It is always greater than 1, sorry. Gamma is always greater than 1, and from this I understand that it's an adiabatic elasticity would be greater than the isothermal elasticity. Now let's understand and let's calculate the adiabatic elasticity and the different elasticity for the different process as well. So let's find out the isobaric elasticity of a gas. How will you do this? So B is equals to minus of delta P divided by delta V by V. While in the isobaric process, pressure of a gas is constant. So if pressure is constant, minus delta P is 0, and so the isobaric elasticity of gas is 0. Next, next, it's an isochoric elasticity of gas. When I say isochoric, what does it mean? What does it mean? It's change in volume equals to 0 or volume remains the constant. So when I write this, it's a B that would be equals to minus of delta P divided by delta V by V. As this delta V by V is 0, this is equals to infinite. It's an isochoric elasticity of a gas. I hope this is clear. Was it? Was it? One more thing. One more thing. If I have been asked that find bulk modulus of of perfectly rigid body, find out bulk modulus of perfectly rigid body. So we understand that for perfectly rigid body, delta V is equals to 0 because they are not going to change its dimensions. That is what we understand by the perfectly rigid body. So this could be written as B is equals to minus of delta P divided by delta V by V. And in this situation, delta V equals to 0. That means B is equals to infinite, or B tends to infinite. It would be a very large if we define it. We define it for a perfectly rigid body. I hope this is clear. Is it clear? Is it? Are you sure? Ready for the question? Are you ready? Let's have a look. The question says that find out find out bulk modulus of elasticity, bulk modulus of elasticity for diatomic gas, at STP. It's a standard temperature and pressure. So it's a bulk modulus of elasticity. It's a bulk modulus of elasticity for a diatomic gas at STP, or I should say find out adiabatic bulk modulus. Find out adiabatic bulk modulus of elasticity. So B adiabatic would be given as gamma times of pressure. They have asked at the standard temperature and pressure, so it would be a 1 atm, or it's a 1.01 into 10 to the power 5. So which gas it is? It's a diatomic. So diatomic is having the gamma that is equals to 7 by 5 multiplied by it's a 1.01 into 10 to the power 5. So this is equals to, it's a 1.4 multiplied by 1.01 into 10 to the power 5. It's a Newton per meter square. I hope this is clear. Is it clear? Are you sure? Are you? Great. Now let's work for the next question. Find ratio of adiabatic elasticity to to isothermal elasticity for for monoatomic gas. How will you find it out? How will you find it out, the ratio of this two? So I understand that when I need to find out the ratio of this two, when I need to find out the ratio of this two, it's in bulk modulus of, it's a bulk modulus of adiabatic, that is equals to gamma times the pressure, and bulk modulus of isothermal, when I say it's in bulk modulus of isothermal, it's a P. So if I take a ratio of this PP has gone, and the ratio would be only left with the gamma. Now which gas it is? It's a monoatomic. This is equals to 5 by 3, or it could be written as 1.66. So you did it. Great job. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you have any doubts up till now? Do you? Do you have any doubts? No? Great. So let's have certain quick questions. First, it says that isothermal elasticity is equals to, yes, it equals to the pressure. Next, adiabatic elasticity. Adiabatic elasticity is equals to, yes, it's adiabatic elasticity is equals to gamma times the pressure. Next, next, ratio of the adiabatic to isothermal bulk modulus. It's a ratio of the adiabatic to isothermal bulk modulus of elasticity is equals to gamma. I hope this is clear. Is it? Is it clear? Do you have any doubts up till now? Is there anything? Is there? No? Great. So now let's look. Let's look the variation in density having relations with ha- having relation with bulk modulus B. Bulk modulus B. So you need to find out a variation in bulk modulus when density is going to be changed. So what I suppose is that this is equals to B is equals to minus of delta P divided by delta V by V. Now we also know that it's a density is equals to mass by volume, and if mass is constant, it's a rho 1 V1. This is equals to rho 2 V2. So from this I can write it's a rho into V is equals to constant. So this is rho into dV plus V into d rho. This is equals to 0. So this is equals to rho dV is equals to minus of V into d rho. What I want delta V by V, that is dV by V is the requirement. dV by V is equals to minus of d into rho by rho. This is dV by V. So if I replace the value over here in the master relation, I could have this relation that this is equals to minus of delta P divided by delta V by V, and this could be written as it's a minus of delta rho by rho, this minus minus plus, and this is equals to rho into delta P by delta rho. This is the bulk modulus. This is the value of the bulk modulus when density is changes. It's a delta rho, it's a change in density. Shall I rewrite this? Shall I? It's a delta rho, yes. So delta rho, it's a change in density. Rho, it's an original density multiplied by delta P, which is change in pressure. I hope this is clear. Is it clear? Are you sure? Are you? Do you have any doubts? Is there anything? Is there? Great. So now let's discuss a third rigidity, which is modulus of rigidity, which we also call as the shear modulus. So let's have a look. It's a modulus of rigidity, or we can say it's a shear modulus. So if within the elastic limit, the ratio of the shearing stress to the shearing strain is known as the modulus of rigidity of the material of the body, and that could be given as it is the ratio of the shear stress to the shear strain. Now let's consider a cube of material which is fixed at its lower face, and it is acted upon by a tangential force F at its upper surface, having surface area A, as shown in the figure. So from this figure, the shearing force F, this force F, causes the consecutive horizontal layers of the cube to be slightly displaced relative to one another. So as you can see, this was the force acting, and due to this force, this point P has been shifted to P dash, and this Q has been shifted to Q dash. So there is a change in the shape of an object, and this is what shear is all about. So shearing strain, it's a lateral displacement of any layer. Basically, it is a lateral displacement of any layer divided by its perpendicular distance from the fixed layer. So this is equals to approximately tan theta, that we have discussed it even in the previous sessions. So modulus of rigidity, which is denoted by eta, that could be written as F divided by A theta. SI unit of this is Newton per meter square, while CGS could be a dyne per centimeter square, or dimensions of it, it's an M1 L minus 1 T minus 2. I hope this is clear. Is it clear? Is it clear? A very few questions has been asked from this, so we will just look at them, the quick question based on this topic. Let's have a look. First, it says that the ratio of the shearing stress to the corresponding blank is called as the modulus of rigidity. Yes, it's a ratio of the shearing stress to the shearing strain. So it is the ratio of this two. It is the ratio of this two that will call as the modulus of rigidity. Let's look at the second question. The CGS unit of modulus of rigidity is, yes, it's a dyne per centimeter square. This Newton per meter square, it's an SI unit. This is the SI unit of modulus of rigidity. Let's look at next. Which of the following has same units and dimensions? Which of the following is having same units and same dimensions? First, Young's modulus of elasticity, a bulk modulus of rigidity, all this are dimensionally same because they are having the same units. So all of the above is the correct answer of this question. I hope this is clear. Is it clear? Is it? Are you sure? Great. So let's wind up this session over here. This was all the rigidities. We have started it with the thermal stress, and we have completed it on the bulk, on the rigidity, or I should say it's a shear modulus. Please go through it. Many information has been hidden between two lines of the NCRT textbooks, so please go through that textbooks as well, because this is a unit which is a very shorter one. Almost it's a unit of, I should say it's a 4 or 4 and 5, probably 5 or 5.5 hours, but this is having one of the question hidden within it. So please go through this, please revise this, please go through the NCRT sections as well, because there are so many theoretical details are there that can be asked, because NTA is going to take an examination. So please go through it. This will help us. This will help us to get good numbers. Thank you. Have a good day. Take care. Bye bye.